Hello and welcome again to the Academy, and this is a continuation of the series of Cal 3 video lessons. Today we'll be talking about directional derivatives. So, a little while ago, a few videos ago, I talked about taking derivatives of multi-variable functions of several variables, and talked about how you could take the derivative of a function like this in the x direction and in the y direction using partial derivatives. And so now the question arises, what if I wanted to take the derivative in any direction? Say in this direction like that, which is in neither x nor y entirely. And so before we do that, I just want to have a small review of arc length. So the arc length of a curve in the xy plane, as you may remember, can be approximated by a right triangle. And the Pythagorean theorem says delta s squared will be delta x squared with delta y squared. And then as we get smaller and smaller, the approximation gets better and better, so we get the exact formula: ds squared equals dx squared plus dy squared, or ds equals square root of dx squared plus dy squared. And this, of course, can be done in terms of a variable t as well. ds is parametric y t squared dt, like that. This is an alternate form. So now that we have that, we can proceed on how we take the directional derivative. So, the directional derivative is basically going to be a derivative in some direction u. U is the unit vector in the direction that we want. And so, since the unit vector, the length is 1, and we can write it, if we're going to be writing in terms of direction of the xy plane, is a unit vector like this. We can describe it based on the angle from the origin as simply cosine of the angle from the sine of the angle. And those are the x and y components. As you can see, so now we have a function here. A point here, x, y, and there's the point of the function, and we want to take in the derivative derivative in the direction u. Basically, we're going to think about this line right here that passes through u, and that passes through x, y in the direction of u. And we're going to try to find how f changes with respect to a change, a small movement here. That's what the derivative is. We take sort of the limit as delta s becomes really small, the change in the displacement from this point is the limit of delta f over delta s. As delta s approaches 0, this approaches the actual directional derivative, which is also written like this, sometimes written like this, with u over here, or a big D with u in the bottom. And so, how do we calculate that? Well, we know how to describe this line in terms of parametric equations we talked about earlier. So we can say x equals, this is actually x naught, y naught. So x naught plus t cosine theta, well, this is the x component of the vector in the direction of the line is the sine theta. That's what it would be for y. And so now we want to find ds. I know ds is just the square root of dx dt squared plus root of y with respect to d squared dt from right here. And we know now, well, this is a constant, so the derivative with respect to t, that would just be cosine of the angle squared plus sine of the angle squared. I know that cosine squared plus sine squared equals 1, so the square root of 1 dt, so ds equals dt. So now, since we're trying to find this will be equal to, so the directional derivative equals df over dt, because ds equals dt. And we know this from the previous lesson. This is just a chain rule for multiple variables. For it. So that's just chain rule for several variables. And now we know that the root of x with respect to t, again, this is cosine of the angle. Plus of respect to y times, well, there's a sine of theta, the derivative of y with respect to t. And now we can see that this is equivalent to, well, see, this is cosine theta, sine theta, and here's cosine, here's sine. And so we can actually say this is the dot product of this vector, cosine theta, sine theta, and also the partial derivatives. These are here and there, and we see that these two are equivalent by definition of dot product of two vectors. And we know this is just our unit vector that we began with dot product, and this we talked about a few lessons ago is the gradient of f, which is just the vector of the first partial derivatives. So in fact, the directional derivative in the direction u, where you use a unit vector, means length equals 1, is just the gradient dot product with that unit vector. And a corollary of this, I guess, something that results from this fact is something I mentioned earlier, that was how the gradient points in the direction of largest increase. And so, with the question of which directional derivative, or which direction, or which angle, for example, will give us the highest rate of increase, is a question of how do we maximize the directional derivative of f, which we know is gradient of f dot product with the unit vector in that direction. And we know that this doesn't change, the only thing that changes is in direction. So we're trying to find which is the maximum direction. Well, we know the dot product by the alternate definition is really the magnitude of the two vectors multiplied times the cosine of the angle between them. And so, just for the sake of example, say the gradient looks like this, and we pick our u to be like that, and this is the angle between the two. And so when is this going to be largest? Well, we know the length of u is just equal to 1 because it's a unit vector. And so when is this going to be largest? When is cosine largest? Well, cosine equals the maximum value of 1 when a phi equals 0. So basically, when they're pointing in the same direction. So when you take the derivative in the direction of the gradient, you'll get the largest directional derivative. So the gradient points in the direction of the largest increase, and its magnitude, the length of the gradient, also corresponds to, because cosine of 0 equals 1, the directional derivative at that point. So if you want to know what is the directional derivative at a point when the directional derivative is largest, well, it's just the magnitude of the gradient. So let us do an example here. Let's use one of the functions that we are pretty familiar with by now. F of x comma y equals x squared plus y squared. And we should know what that looks like by now. It looks something like this. And say I want to find the directional derivative and direction of u of, at the point, say 1, 2. So the point 1, 2 is 1, 2 right here. And so the derivative, let's say we want to find it in the direction of, I don't know, let's say u is going to be the direction of -1, -1, but this is not exactly the unit vector. We have to scale it down. So it's divided by its length. That would be, this is just 1 squared plus 1 squared, or -1 squared is 1, 1 plus 1 is 2, so it's just -1 over square root of 2. And so in that direction, the derivative of this function is going to be the gradient of f dot product with u. And the gradient, as we know, well, the partial derivative with respect to x, that's just 2x. And then with respect to y, it's 2y. And the point was 1, 2. So that's going to be 2, 4, dot product with -1 over square root of 2, -1 over square root of 2, which is -2 over square root of 2, minus 4 over square root of 2, which is negative square root of 2, minus 2 square root of 2, that's -3 square root of 2. So that is the derivative of this function at the point 1, 2 in the direction of this -1, -1, or -1 over square root of 2, -1 over square root of 2. And that is all I have for directional derivatives. Thanks for watching, and I'll see you in the next video.